All right. Hear anything until just now?
All right, can everyone hear us now? Thank you for those in the chat to let us know. And I will start over. Okay, so again, thank you all for coming to our very first Tap Talks virtual happy hour. I do hope all y'all will get a drink and enjoy this discussion. So recently there was an article that not everybody, but it was shared widely in social media. It was getting a lot of attention, and it was about parallel universe discoveries, apparently. And so this had to do with neutrino physics. And at UT Arlington, we have a whole department dedicated to neutrino physics. And so we have Dr. Asaadi, Dr. Jones, and Dr. Woodruff, who are working at UT Arlington with neutrinos. And we also have guest speaker Ibrahim Safa, who was featured in a lot of the articles. Multiple of his quotes were taken and used, and he was the first author on one of the papers that was used.
I'm here.
The sound's still not working?
No, it can. The comment section claims we can hear us.
Okay, sorry. Yeah, so Dr. Jones is going to give a quick talk. He's going to explain the experiment and what was actually found and what can be understood about it. And then afterwards, we will have discussions between all four of the panelists. And any of the questions that y'all want to have, whether it be about this experiment, about neutrinos in general, I do encourage you to ask. And this is your opportunity to get them all answered. And so, Ben, when you were ready, or Dr. Jones, if you want to share your screen, and we will get started.
It should be sharing now. Can it be seen?
Yep, it's perfect.
Good. Okay, hello everybody. This is the flyer for this event. Thank you for joining us for this experimental Tap Talks happy hour. Obviously, we'd much rather be in a local microbrewery, which is where we typically do these events, where we talk about science and drink beer together. But we can't do that given the circumstances. And we thought it would be fun to get together and drink beer and talk about science virtually. So cheers. Please pour yourself one if you're of drinking age. Well, and if you like beer, I suppose, but get yourself some kind of beverage for this talk anyway. And let us tell you something about this recent news story that broke all over Twitter and the tabloids about a supposed discovery of parallel universes. So this is the story in question, and the place where I first became aware of it was the New York Post, this esteemed newspaper. And the headline of this story was that NASA scientists had detected evidence of a parallel universe where time runs backward. And so there's a fancy video here that has nice computer graphics. This thing in front of us, I guess, is evocative of a black hole. We actually
already have a question, which I think is pretty important for the start of this talk. And it is, how can parallel universes be real if our neutrinos are not real? So if you want to discuss real quick if neutrinos are even real.
Yeah. So neutrinos are for sure real. Neutrinos exist. We discovered them in 1955. They're emitted copiously from the sun. They're emitted from nuclear reactors. They're produced in particle collisions in the atmosphere. And there's actually a major ongoing program that not only routinely sees neutrinos, but studies their properties in great depth. And this is a program that we're involved in at UTA. And so I'll talk about some aspects of this later in the talk, but let me continue and we'll go on. We can talk about that in the panel discussion as well. But okay, so continuing. Please do keep your questions coming though. I don't mind being interrupted. So the headline is that NASA scientists have detected evidence of parallel universes where time runs backward, and this is the story. So the story begins in a scenario straight out of the Twilight Zone. A group of NASA scientists working on an experiment in Antarctica have detected evidence of a parallel universe where the rules of physics are opposite to our own, according to a report. And like I say, there's a fancy video. You can see that just over the top of this screenshot of the video is up next, equally important breaking story for the New York Post that Cat takes virtual ride on Splash Mountain during lockdown. Anyway, this is the story, and it first came across my desk when I saw it on social media. And so I kept reading because obviously I'm a particle physicist, and it's quite important if somebody has discovered parallel universes that I'm aware of this, because it's going to affect my thinking about physics. And the story goes on that low-energy subatomic neutrinos, so the plot thickens here because I'm a neutrino physicist, so if these particles are really showing evidence of this new kinds of physics, it's certainly something I should be aware of. But these subatomic neutrinos with a mass close to zero can pass completely through the Earth, which is true. I can verify that's true. But higher energy objects are stopped by solid matter in our planet, according to the report. Then the next step is that this means that high energy particles can only be detected coming down from space, which makes sense because the ones coming up through the Earth should be stopped by the Earth. But the team ANITA detector detected the so-called tau neutrinos, which come up out of the Earth. And then there's kind of a major leap of logic here that says this implies that the particles are actually traveling backwards in time, suggesting evidence of a parallel universe. And obviously, this is quite a leap of logic. And so I wanted to understand where this particular story was coming from and what kind of scientific report had produced this information. And so on the left, you can actually see a picture of the detector here. It looks like it's kind of magically levitating over the ice. It's not. There's a crane at the top, which is off view. But this is an experiment that I'm familiar with and have spent much time understanding the data from, which is the ANITA detector, which I'll be talking about in this talk. So I kept reading this article, and actually my attention was even further piqued. First of all, it's claiming a major physics discovery. Secondly, it's claiming a discovery involving neutrinos. And then thirdly, it had a quote from Ibrahim Safa, who in fact used to be my student at UTA. So Ibrahim is now working with the IceCube Neutrino Observatory in Madison, Wisconsin, but he used to be working with us at UTA, also on IceCube and on NEXT. And I'm pretty sure he doesn't work on the ANITA experiment, which he's quoted as working on here. And I'm also pretty sure he didn't discover a parallel universe, or I feel like he would have told me about it. So I quickly called up Ibrahim, who is going to be part of the panel discussion later, to find out what was going on. So Ibrahim and I have worked on various neutrino physics experiments, and we're no strangers to our work being in the media. This is an example. Our work searching for new particles, new kinds of neutrinos, was featured in the Wall Street Journal recently. And in this case, this is a great headline too. Theorized particles may not exist. I guess there's no headline I can imagine with less information content than that one. But this particular study was one that we did that looked for some kinds of new physics and did not find it, but did not find it in a particularly compelling way, using the particle interactions in the ice in Antarctica. And so we had this story in the Wall Street Journal. So both of us are familiar with talking to the press and these kinds of things. So I was compelled to understand why Ibrahim gave this quote to the New York Post about this supposed discovery of a parallel universe. So not long after speaking to him, he pointed me to this article, which followed up in Forbes. So Forbes had picked up the story from Twitter and from the New York Post and the Express and a couple of other tabloids. And they decided to deconstruct what the truth is behind this headline. And Ibrahim was also quoted in this article in a couple of places, this time through his tweets. And so here's his first tweet, which is that NASA has discovered that you all should not be getting your news from the New York Post, which I thought was pretty funny, actually, kind of a sick burn there. And I also much appreciated the use of the word y'all, demonstrating that he's a true Texan at heart, like myself, as you can tell from my accent. And then he went on with his brutal string of tweets within the Forbes article, which this one's particularly funny. We looked at these ANITA events and they can't be standard neutrinos. They're probably just a result of our imperfect understanding of the Antarctic ice, but there's a chance some new physics phenomena is responsible, to which the tabloids reply, parallel universe with multiple exclamation points. So, okay, this story is like clearly unraveling in front of me here.
And
so
if I could, just to jump into sort of this, to add a little bit to what I appreciate about what you're saying here. I like that the first tweet where Ibrahim gives this burn is at midnight, and then 7 hours later he wakes up with a very sensible burn to follow on the same report. So it just, there's some tact in his Twitter use that I greatly appreciate.
That was a graduate student for you.
Really working the news cycle, I think.
That's right.
Yeah.
For the record, I had like 10 followers before this. I was mainly tweeting for myself.
How many followers do you have now?
Oh, they just broke 1,000 or so.
Oh my goodness.
Yeah.
15 people were talking about your tweet here as well. Okay, so you're Twitter famous. Congratulations. Okay, but anyway, I wanted to understand what the science was behind this claim, because my presumption is that what the journalists here had done was found some real story and then misunderstood it and misconveyed it. And so I wanted to understand what the original story was that they'd misconveyed, because I certainly wasn't up to speed with it, whatever it was. And so I'm actually fairly familiar with neutrinos interacting in Antarctica, because I work on this experiment. And in fact, our group at UTA is the only group in Texas that works with this experiment. This is the IceCube Neutrino Telescope. And the IceCube Neutrino Telescope, here you see it sitting on top of the ice. This is actually just a box of computers which transmit data to the north, where the north means anywhere except the South Pole, which is where this is. But what this device is actually is it's reading data from 5,160 very sensitive light detectors, which are under the Antarctic glacier. And so these are distributed across a cubic meter of ice, which is 1 billion tons. And they detect very small amounts of light that could be emitted in the ice. And they do this in order to detect very high energy particles interacting in the South Pole Glacier coming from outer space. And so the way they make this detection, so that those of you who have seen the HBO series Chernobyl will be familiar with the fact that nuclear reactors glow blue. And they glow blue because there's a kind of light emitted when highly energetic particles move through a dense medium, and it's called Cherenkov radiation. That's what this blue glow is. And in fact, the particles moving through the ice at the South Pole also emit this kind of same blue glow. And through detecting this blue glow, we can identify that charged particles were produced in the ice from some interaction, and then try and reconstruct the properties of the original particle that created that deposit. And so this is an example of one of our events. This is a real detected event from an astrophysical neutrino. This is a neutrino with an energy of about 1 peta-electron volt, which for particle physics is a very, very large amount of energy. And what happened here was something called an electron neutrino, or maybe a tau neutrino, interacted in the ice, and then it produced a cascade of charged particles. Those charged particles emitted that blue nuclear reactor type Cherenkov radiation. And then these balls that you see here show where and when inside the array we detected the radiation. So a large ball means we detected lots of light, and a small ball means we detected not very much light. And you see the light kind of spreading out from the interaction point. This image is slowed down quite a lot, by the way. This video takes probably microseconds, in fact, in practice, but it's shown here taking several seconds, so you can see the light spreading out. This detector is very big, and these events are like the size of a city block. So this is the same event overlaid on Madison, Wisconsin, which is where Ibrahim is sitting right now, I guess. We could probably see your house, I guess, Ibrahim, where you are on this picture. And you see the sort of scale of these particle interactions that we're detecting. So what these objects are, these very, very highly energetic particles interacting in the ice at the South Pole.
I actually have another question, if you don't mind.
No, I didn't mind.
Is it possible for antimatter to be traveling forward in time instead of backwards in time?
Let me get to that at the end.
Okay.
Let me get to that at the end. Yeah. Okay. So remember it and then ask me at the end. So okay. So these very high energy particles, where they come from is still relatively unclear, but it's becoming clearer all the time. And in fact, there have been some major discoveries from the IceCube Neutrino Telescope in the last couple of years, which I'll touch on in a minute, which are beginning to make this clearer. But what seems to be happening to accelerate these particles is that something like this object, this is a black hole devouring a galaxy. So as the galaxy falls into a black hole and gets devoured by it, the gravitational potential energy that the matter used to have when it was far away from the black hole gets turned into kinetic energy. So if you like, you just imagine this this black hole, and it's pulling something towards it, and the thing it's pulling is getting faster and faster and faster. So you're just getting more and more and more of this kinetic energy and heat near the middle of the black hole. Now, because these galaxies are disks, it means it's very dense to go sideways. So the energy from this process cannot escape sideways through the disk. It can only escape out the perpendicular to the disk. And what that results in is these very, very highly energetic, relativistic beamed jets that shoot out perpendicular to the disk of the system. And these jets occasionally point at us on Earth. And when they point at us, we call that a blazar. And that can shower us with extremely highly energetic particles, which very occasionally interact inside our particle detectors. And so this is one especially interesting one of those events. This was detected a couple of years ago by IceCube. And this is the first one of these events where we think we know the actual blazar that produced it. Because what we can do is trace back the direction this came from, and then we compare our data to data from a different telescope. In this case, this is the Fermi telescope. So Fermi had been watching one of these sources emitting gamma rays, which are very high energy photons. And Fermi had been seeing a low level of activity over a long time. And then suddenly there was a period of great activity. So the black holes started feeding much, much more on the galaxy. Like matter fell in at a much higher rate than it had been falling in before. And it turns out that that period of very strong activity was exactly the time we saw this very high energy neutrino coming from the same direction. And so this is a relatively significant observation that we may have seen the actual source of one of these ultra high energy cosmic neutrinos coming from a black hole that's eating a galaxy. So this is what all these particle detectors, including the one that the story claimed discovered a parallel universe, are looking at, are these kind of very high energy neutrinos made in violent astrophysical objects, probably black holes devouring galaxies. Now, I've described all these things so far as telescopes. And if probably what you have in your mind when you think of a telescope is something like this. This is the kind of telescope that Galileo or Newton would have been familiar with. And obviously you look through this device and it makes distant objects appear closer. But telescope nowadays means something much more general. It just means something you can use to observe the universe at great distances. And so both of these things, the IceCube Observatory, 1 billion tons of ice with light detectors, and the Fermi satellite, which is basically a box of electronics that floats around on a satellite detecting gamma rays, because they are imaging these distant objects, they are, in a sense, telescopes, even though they don't look very much like the one that Isaac Newton or Galileo would be familiar with. The reason we have all these different kinds of telescopes. Yes.
1 second. So this question is from Dan Sosa. How often do these blazar events hit Earth, and how often are they detected?
So the astrophysical neutrinos, we've seen about 50 of them, roughly. I forget the exact number. We update it periodically, but we've seen a few tens of them. But so far, there's only been one where we've been able to point it back to the source that produced it, which was this one I showed. Is called the TXS event. It has a long catalog number, which is what the Fermi Space Telescope uses to catalog that object. But that's the first time that we've ever been able to pinpoint one of the astrophysical neutrinos back to the blazar it came from. And we hope we will see more with the next generations of the experiment.
But blazars are pretty common, right? If I remember, there was some story of satellites trying to be used to detect nuclear activity on Earth that was actually set off by these astrophysical events coming off and giving false readings in these satellites.
Yeah,
remembering that story correctly?
That sounds to me a bit like gamma ray bursts, maybe.
Maybe I'm thinking of gamma ray bursts then.
Yeah. But blazars are not uncommon. I don't know how many of them there are in the universe, but the universe is big, so there's a lot of them.
We've detected several thousand of them. I think over 4,000 blazars are in the Fermi catalog, but not all of them are just electromagnetic detections. So there's no neutrino detections yet, except for this source that you talk about, the TXS source.
Thank you, Ibrahim. Very good. So, okay, good. But anyway, so there's all these different kinds of telescopes that image in all kinds of different wavelengths and modalities. The big thing right now in the field is called multi-messenger astronomy, which means using not just light, like most telescopes collect, but also neutrinos, gravitational waves, anything you can put your hands on that the object is emitting. But just to give you, this is a nice illustration that shows you why we have all these different kinds of astronomy and different kinds of telescopes. So these 4 pictures of astrophysical objects are actually all the same object. This is an object called the Crab supernova remnant. It's what's left behind after a supernova explodes. So a star explodes to produce a supernova, and this is what's left behind. And what you're seeing here is pictures of what was left behind from that explosion in different wavelengths. So you see the X-ray is giving you a very deeply probing high energy map of the deep structure of the object. Optical is showing you something about fluorescence of the hot gas around the outside. Infrared is showing you the heat. Radio is to some extent also showing you the heat, but in a different way and in a different temperature scale. But you can see by putting all this information together, you learn a great deal more about the physics that drives these astrophysical objects. And that's why we have these different kinds of telescopes. So the picture at the bottom right there, the purple one, would have been taken by a telescope that looks something like this. So these are all individual satellite dishes, and they're all detecting, it looks like they're all separate telescopes. But in fact, this object is actually one telescope because one radio wave comes across this device and interacts with all of the telescopes simultaneously. And it's called an interferometer. That's how these radio telescopes work. So this is an example of a radio telescope. And we've learned a great deal about the universe from observing radio waves, and not just an enormous amount, about all kinds of different things. And this is what a sort of traditional radio telescope looks like. It's a bunch of satellite dishes all spread out over a large area and then doing this interferometric detection. The detector which produced this supposed parallel universe observation is also a radio telescope, but it's a very different kind of radio telescope. In fact, it's the only one of its kind, at least as far as I know. And this is a picture of that particular radio telescope. So these things here, these white things, I don't know if you can see my cursor on this feed, but the white things here are kind of like the same as these satellite dishes. They're detecting the radio waves coming inwards to this device. But the interesting thing about this device is, while this radio telescope looks up into the heavens for radio waves from space, this device looks down into the ice for radio waves coming from the ice. And so it flies up on a balloon, and they lift off from some base in Antarctica. They lift off from the McMurdo base, which is the main US base in Antarctica here. This is a map of Antarctica. So this is the main US research base. The balloon lifts off and then carries this downward-looking radio telescope, and it just blows around on the wind. The wind in Antarctica goes round in a circle because the Earth is spinning, so that's how the wind pattern works. And so the first week it went this far with the red line. The second week it went round the blue line. The third week it went round the green line. And then they wait until it's hopefully near some kind of populated place on the continent and then crash it into the snow and then go to collect it to take the data off and see what it saw from using radio telescopes looking down into the ice. So in this particular case, it kind of got relatively near to the Amundsen-Scott station, which is at the South Pole, which is where the IceCube telescope is. They brought it down and then went to collect the data from the device and see what's there. So the kinds of events that this radio telescope detects look like this. And obviously to most of you, and in fact to me as well, these just look like crazy squiggles. But to the people who work on this experiment, these don't look like crazy squiggles. They have a very complicated set of software packages and algorithms they apply to analyze this data and then interpret what it means in terms of detection of radio waves from the ice that suggest particles were interacting inside the ice. And so just to give you a sort of schematic here.
Dr. Ince, there's a slight lag between the YouTube, so it's just, if you don't mind going back to the ANITA balloon, the question is, how do they do that? How do they take the balloon down? You say they crash it down.
Yeah, they have control of the balloon remotely, and they can release the helium and then bring it down to the ground. So they just, like a normal hot air balloon, they let the gas out and then the balloon comes down. Gently, hopefully. They're never quite sure it's going to land and not break, but so far they've been able to recover the payload every time. But there's always a chance it's going to come down and crash into a mountain and be unrecoverable. But they've flown it 3 or 4 times now, and in all of those 3 or 4 times, they've successfully recovered it.
Which I'll also just wanted to side note here. I've gotten to ride in a hot air balloon as like a tourist ride. And before they get on, they also tell you, look, we're never sure where we're going to go down or how soft it's going to be or if everything's going to be okay. Do you still want to go up? So what is true of Antarctic ice balloons is also true of humans and air balloons.
Yeah.
Which is terrifying.
And I guess they could also add, P.S., if we go down over here, it's 3,000 kilometers away from any population.
Yeah, exactly.
Yeah. Okay, cool. So anyway, yeah, this is what it detects, and then this can be reconstructed into being radio emission from some particle that's interacting in the ice. So this is why this radio telescope looks down, not up, because what it's looking for is a high energy particle that interacts in the ice. The products of that interaction emit radio waves. Those radio waves are then detected by this radio telescope, and then something can be said about what this particle was that interacted inside the ice. Okay? And these particles in practice are always neutrinos, because they have to penetrate through enough of the ice to give a detectable event. So, okay, now there's a problem, because one of these events in ANITA I'm showing here is not like the others, and none of us can tell just by looking at this which one of these is not like the others. But one of these events comes from a very, very high angle like this after they reconstruct it. So it's a particle that was like coming through the Earth, and instead of doing like a glancing blow like sideways across the top of the Earth, it came in at a very, very high angle with a very high energy. And the problem is that all the known particles in nature, like the neutrinos and every other particle, with energies this high, they would be stopped by the Earth like a brick wall. They would interact very, very far back across the Earth. They would never make it to Antarctica at this very steep angle. And so this is an event that can't be explained in terms of known particles. Okay. And so we've known about this for a while, the community. It's a few years old, this observation, and it's one of these strange mysteries that we suspect may be some evidence of something interesting, or maybe just an instrumental effect. It's something that's certainly thought-provoking and that we're exploring. So this is where Ibrahim actually got involved in this story. He wrote a paper on the collaboration that I work on IceCube, that says if this was really a high-energy astrophysical object, like a feeding black hole shooting neutrinos at us, then IceCube would for sure have seen it, like really, really brightly. Don't worry about what this figure shows. I just snapped a cute figure from their paper. But the message is that IceCube, the detector we work on buried in the ice, should have seen an absolutely enormous flux of particles if this is really what this is, some feeding black hole beaming at us. And so just to give you an idea of how powerful a source that would be, here's an animation that Ibrahim prepared. I'm just joking. It's not really that violent, but it would sure be really, really bright. We would see it very clearly. And so the question is then, what is the explanation? It's obviously not just a normal neutrino, because it's gone through this very high angle, and it's obviously not evidence of a new astrophysical source, because we should have seen that source in other detectors. And so there's two options: either something exciting, like new physics path to discovery beyond the standard model, and there's various papers about this, or something less exciting, like we don't understand the way the radio waves interact in the ice very well. And people have been writing papers on all of these. I just took 3, but there's many papers being written about how to understand this event. But I just want to remind, before I go on to this slightly crazy paper that prompted the New York Post article, about the scientific method. So the scientific method works in the following way. You do experiments to test predictions of your model. And the best model we have in particle physics is called the standard model. It's enormously precise. It predicts some things to 10 or 12 decimal places of accuracy. And it explains pretty much every effect that we observe in the universe, with a very small number of exceptions. And those exceptions are what drive future research to hone the model more. But you test the standard model in every way you can. And if you observe something that doesn't agree with your predictions, then you come up with a well-motivated theory. And that theory then is something that has to be used to make more predictions. And then if you test those predictions and the theory passes, then you've made a major discovery. But just coming up with a theory that explains the anomaly is not itself a discovery. You have to then test the other predictions the theory makes. Okay, but all of this is part of the process. So at least in my group at UTA, I encourage everybody to be part of every step of this process, to be part of the step where you measure the standard model, to be part of the step where you come up with new explanations for the things that have been observed that you can't explain, and where you figure out what the predictions are of those and test those predictions as well. I mean, a good scientist should be involved in every step of this process. An example of a model that's been tested very well, and at this point is established, is the Big Bang. So the Big Bang, so there's a famous, everybody says the Big Bang theory, partly because of the TV show, but also it's just somehow gotten sort of welded to popular culture, this word, the Big Bang theory. But at this point, the Big Bang theory is not a theory. The Big Bang is an empirical fact. At one time, the Big Bang was a theory. And it was a theory when Edwin Hubble, in the early part of the 20th century, was looking at the color of stars in different places in the sky. And he found that the stars that were further away from us were redder, generally, than the stars that are near to us. And one way of explaining this is that the light emitted by things that are moving away from you tends to be stretched and moved into the red end of the spectrum. This is called redshift. And so one way of explaining that the stars far away are redder than the stars nearby is that everything is expanding, the universe is expanding. And if the universe is expanding, the things further away are going away faster than the things nearby. And that would explain this famous Hubble plot. Okay. So obviously, if this is really what's happening, the universe is all expanding away. Naturally, it used to be smaller before than it is now. And so you come up with the Big Bang Theory. Like if the universe used to be smaller, then at some point it had to be very hot and very dense with all the energy and the matter and everything in a very small space. And so you would hypothesize then, in theory, that it could have started from a single point and then expanded from this very hot, dense region. Okay. And so this is where the Big Bang Theory logically first emerged from in science. But since then, the Big Bang Theory has gone from being a Big Bang Theory to a Big Bang phenomenon, a verification. And it was first verified by Penzias and Wilson. And essentially, this theory that everything used to be in a very hot, dense region makes another prediction. So as well as everything moving away from each other now, this also predicts that there should be a bunch of radiation filling all of space. And that radiation would have a particular temperature, and it should be observable. And so Penzias and Wilson built this crazy horn thing in 1959, and they observed this radiation, which validated the Big Bang hypothesis. Now, interestingly, we still study this radiation today. By the way, those of you who remember TVs that used to do this before we had LCD displays, this is evidence of the Big Bang radiation in itself. But nowadays, we have actually very powerful satellites that don't only see the Big Bang radiation, but they measure it in incredible detail. And this picture at the top is a famous picture from physics from the Planck satellite. This is showing you the temperature of the Big Bang radiation in every direction in space. So this is towards the middle of the galaxy, and then this is like away from the galaxy, but it's looking in every direction and looking at the fluctuations. And actually, it turns out that the Big Bang Theory doesn't just predict this radiation exists, but it predicts the size of those fluctuations with part per million precision. And indeed, in understanding these fluctuations and measuring them with these satellites, the Big Bang Theory has been validated with like sub-part per million precision at this point. So this is no longer a theory, it's a model. I mean, it's an established fact. Okay, so something that's not an established fact is this model, which is the one that this New York Post article was getting excited about. So there's a model that has been developed to try and explain something about why there is this strange dark matter in the universe that I'm not really talking about in this talk. But there's a model that's been developed that suggests that as well as a Big Bang running forwards in time, there could have, at the same time, been produced an anti-Big Bang that was running backwards in time. And so the moment of creation of the universe was not just the moment where the universe emerged coming forwards, but simultaneously a forwards in time universe emerged and a backwards in time universe emerged. And there was a Big Bang and an anti-Big Bang going opposite directions. And this is called the CPT symmetric universe. And basically through some very complicated scheme of logic, which I've illustrated on this right-hand picture here with this machine here, supposedly one of the predictions of this anti-Big Bang universe is that you could have these kinds of strange events that were seen by ANITA. And Leslie begged me not to read the sentence, but I'm just going to read it anyway, because I just want to say all the words. So the way this is explained under this model is the dark matter particle is a 480 peta-electron volt right-handed neutrino that decays into a Higgs boson and a light Majorana neutrino. The latter interacts in the Earth's crust to produce a tau lepton that in turn initiates an atmospheric upgoing shower. So here are the steps in this process, right, to explain these events. So this is a very complicated and sort of difficult way of explaining an in principle quite simple observation. And I want to say, in my opinion, this is very likely not how the universe works. Okay, it's a hypothesis, but the thing is, it's a valid scientific hypothesis because they do give us a way to test it. In fact, at the end of their paper, they say the second generation of the Extreme Universe Space Observatory to be flown aboard a super pressure balloon in 2022 will monitor the night sky in the southern hemisphere for upgoing showers emerging at large angles below the horizon, and it will provide an important test of both the unusual ANITA events and the ideas discussed in this letter. And so it's sort of, in some sense, it doesn't matter whether I think that this is a likely to be true. What matters is it's a hypothesis. I'm almost at the end, Leslie, so I'll do the presentation. But what matters is that it's a hypothesis, and it's a testable hypothesis. So this makes predictions, and these predictions can be tested in future experiments, and then it doesn't matter what I feel, we will find out. However, it is certainly not true that NASA scientists have detected evidence of parallel universes where time runs backwards. What was detected were two strange events, and then after the fact, some scientists came up with a model which predicted that perhaps these could be explained in some way, and that way is testable. Okay? And we will find out whether in future experiments whether there is any validity to this. But it's also one of many different models. You can cook up all kinds of different models that will make this prediction, and if you make ones that are testable, you're doing good science. So yes, no, this is not true. And so I'm just going to finish with this nice quote that I found. Well, in fact, my graduate student Nick found this quote from John Mulaney. The New York Post is my favorite newspaper. I think it's great. I read it every day. I like reading the New York Post because reading the New York Post is like talking to somebody who heard the news and now they're trying to give you the gist. It's like you get the same amount of information if you grab somebody on the street and you were like, hey, what happened today? And I guess in this case, this quote finishes with the guy on the street says, oh, I don't know. I think some scientists discovered some parallel universe or something. So I want to stop there, and then we'll go to this like panel chat. But one of the things I just want to mention to seed that discussion is that this headline is interesting because, I mean, the headline is obviously false. But the thing that's interesting about the headline is it actually does encode a few things that really are true about our universe. I mean, so this idea of parallel universes is something that really is rooted in quantum mechanics. And the way we understand the universe now in terms of, again, an established, validated phenomena of quantum mechanics, it does involve several universes proceeding in parallel and interfering with each other. So parallel universes in some sense do exist. We know that to be true. Also, this idea of time running backward, while it's not true, while we have not established that there is a universe parallel to our universe with time running backward, there are objects in our universe for which time does run backwards. In fact, some of you may have heard of antimatter. So one interpretation of antimatter is that it's actually matter moving backwards in time, and that's a completely consistent way of understanding the physics of antimatter. So while this story itself is not particularly well researched or true, there are certainly elements of it which do hint at exciting things that we really do believe to be true about our universe, and maybe we can talk about those in the Q&A. So thank you for your attention. I'll imagine your rapturous rounds of applause. So I hand it back to the moderator now, right, Leslie? Do we still have Leslie?
We do, but she doesn't know that she's muted.
Okay.
My bad. I was talking to myself. Okay, so yeah, we have quite a few questions. Most of them are panel questions that I think it would be interesting to hear different viewpoints on it. I do want to go back to some of them that were asked during your talk. And so one of these by Jacqueline Johnson, is it possible for antimatter to be traveling forward in time instead of backwards in time?
Are you going to assign them to someone, or do you just want us to dive in?
Please, everyone, just volunteer and dive in when you want to. Okay.
Somebody else want to do that one? Because I just did the talk.
I mean, I guess to me that when I read that question, I thought to myself, like, it all depends on what we mean by forward in time or backwards in time, which are sort of these arbitrary labels that we've applied. It's in the same way of saying like this is matter and this is antimatter. I don't think I'm getting to the spirit of the question, but it does feel like there's a certain amount of like, yeah, we can call them whatever we call them in terms of going forwards and backwards.
I mean, maybe I'll have a go at it. So in this particular way of understanding antimatter, it's called the Feynman-Stuckelberg interpretation. Like probably some of you have heard of Feynman. Probably none of you have heard of Stuckelberg, I guess. I don't know who he is apart from that, actually. But in this particular interpretation, there's only one kind of stuff. And that stuff, if it's going forwards in time, is called matter, and if it's going backwards in time, is called antimatter. So in that sense, all of the stuff going backwards in time is antimatter by definition, if you like. Now, I guess this gives a nice segue to talk about something we work on actually in my research group at UTA, which is about Majorana neutrinos. So it's possible to have a kind of stuff which is actually going forwards in time and backwards in time at the same time. The only kind of particle that could be this is the neutrino, and that's actually one of our main research thrusts at UTA, is trying to establish whether the neutrino is indeed simultaneously going forwards in time and backwards in time, unlike everything else. And so, yeah, I'd be happy to talk more about that later if people have more questions about it.
All right, so this next question, I think it has several parts to it. I will read it, and then I will break it up if y'all want me to into parts for different people to ask. So this is by CK. If parallel universes do exist, do you think their universe can only observe left-hand or sterile neutrinos, not right-hand? Or will it be a different version of our right hand? And so I think it might be good to kind of, if you can, kind of explain sterile neutrino, left-handed and right-handed neutrino, and how that would change in a parallel universe.
Leslie, pick someone for the question. So then we don't have to wait.
Well, let me say something here, because it really depends on what kind of model you're talking about, right? Because in the sense of this CPT symmetric universe, these right-handed neutrinos would come out from this parallel, well, would fall out in the math from this parallel universe that you hypothesize. But I don't know about in quantum mechanics, like you were talking about, Ben, where it's several universes in parallel interfering with each other. I think there you would have to assume that it's copies of the same thing, and not necessarily certain handedness is only exist in certain universes, right?
Yeah, the parallel universes implied by quantum mechanics, or parallel histories, if you like. The way to think about it there is that there's various ways that the history of the universe could go. And whereas in classical physics, we would understand that it picks one and goes that way, in quantum physics, it kind of goes all of the ways it can go simultaneously. And you don't normally notice that, except when those different ways interfere with each other. And so in that sense, when you have a sterile neutrino, actually, if you have a neutrino produced in some event and it propagates and then interacts, one thing that could have happened is a neutrino could have been made that was sterile, or one thing that could have happened would be a neutrino was made that was not sterile, or with different kinds of neutrinos being made. And actually, the interference between those histories of the universe does give an observable phenomenon that we search for. It's called neutrino oscillations. And so we've seen that kind of interference of parallel universes, actually, with regular, not with sterile neutrinos, but with regular neutrinos. We've established that kind of interference of parallel quantum universes experimentally. The sterile neutrinos are a new kind of neutrino, which we've seen some anomalous experimental evidence that suggests it might exist. And we've yet to firmly establish that the interference between parallel universes that would come from sterile neutrinos happens. But we've certainly seen it for the regular neutrinos.
Okay, so I'm going to skip around in the order of chat questions. I'm trying to keep things organized, so I shouldn't miss any of y'all's questions in the chat. I'm just not going in order. So this next question is kind of online with what Dr. Jones was just talking about, but I want to aim it at Dr. Woodruff because it is directly aligned with what she does. And the question is asking, is there any experimental proof of Majorana neutrinos?
Yeah, so far not yet, and there's a huge research program kind of all over the world looking for that, including what we're doing at UTA. So the evidence the most direct evidence that everyone is kind of looking for right now would be this type of decay called neutrinoless double beta decay, where you have an atom undergoing beta decay, where it decays 2 electrons at the same time, which is a standard model process that we know is allowed and has been observed. But if the neutrino is its own antiparticle, if it's a Majorana neutrino, then it's possible that in these events, the neutrinos coming out of this double beta decay, you would have a virtual one that it would basically kind of annihilate itself, and you would only see electrons coming out. So if we observe that type of event, then that would be evidence that neutrinos are Majorana particles. So that's kind of what everyone's looking for right now, but we haven't seen it yet.
Okay, so this next one, I'm not positive who to aim it at. Probably Dr. Asaadi, actually, but the main question, there's a few questions about entropy, and one of them is, did both universes, if it's parallel universes, did they start with low entropy?
The entropy question gets aimed at me. Okay. So we have to sort of talk a little bit about, like, what do we mean here with entropy, of course. And so if you think of entropy as a measure of disorder, then you've got a hypothesis that you can build in here and say, is the early universe going to be less disordered than the older universe? And there are various theories that suggest that the state of which nature evolves is towards greater disorder. So if you've got an arrow of time that's pointing one direction and pointing the other direction, you have to say, well, what gives you that arrow, right? And there are various theories that I've become aware of that suggest that entropy is the thing which gives time its arrow. So the idea there would be these parallel universes, as best as I understand any of this, is you would still have to start from a state of, one type of amount of organization and be evolving towards some other in order to even define that arrow of time. So would the other parallel universe have to be of low entropy? I guess, but I don't know, you're sort of measuring a gradient. And so is one evolving towards a positive gradient, the other a negative gradient? Sort of well outside of my wheelhouse of understanding, but that's kind of how I think of entropy and that idea.
Yeah, I think they both, to my mind, they both have to start with a state of low entropy and evolve towards a state of high entropy. So near the Big Bang, they both have low entropy, and then far away from the Big Bang in time, they have high entropy. Now, of course, one of them in this crazy model is going backwards in time, right? So it's sort of evolving backwards in time towards higher entropy. And so it depends how you want to think about the direction, as if it's getting more entropy, if it's getting less entropic coming forwards in time or more entropic getting backwards in time.
Exactly, yeah.
I guess, yeah. But yeah, I think it's a really smart question, whoever asked that question.
Yeah.
We actually had multiple, but I think you answered all of them by covering that. Okay, so we're going to switch directions a little bit. And I actually feel like, Ibrahim, if you want to answer this one, but all of you are welcome to tell your opinion. And the question is, how do you feel about going to Alpha Centauri?
I would be the first one to sign up if it was possible.
That's what I'm thinking.
I've always wanted to leave Earth. No, I'm kidding. It was I've been a space enthusiast for a long time. It's Alpha Centauri's. There's a mission, the Light Sail mission, I think, is what people are researching right now, and they're trying to use extremely reflective materials that they make in the lab. And that they can then shoot with a laser beam and send at like 30% the speed of light to Alpha Centauri to collect data from there. And I think that's an amazing project that people should keep in touch with. And I think even someone here at Madison is developing the technology at a condensed matter lab. His name is Victor Brar. So yeah, it's definitely an area of research that people are looking into, and it would be really exciting. There's no prospect of human travel to Alpha Centauri yet. We're talking about small chips that we're sending on light sails, so they'd be about this big. But yeah, it's exciting nonetheless.
Awesome. So I'm actually going to take another direction now. So we have a 15-year-old who is asking for some advice, and they would like to know if you have any advice for an aspiring astronomer, and they would like to know how you got to where you are now. And so maybe also mention what part of your career you're at, if you don't mind, and how you got here. Let's start in order. We'll just start in the order I see on the screen. Asaadi, Dr. Asaadi, if you don't mind.
Sure. So whenever I give advice to anybody, I always remind them that you are hearing from people who have gotten to a certain place in their career and probably don't really have any deep knowledge of why they succeeded and others maybe didn't. So there's this thing called the survivor bias that you should always be aware of when you're receiving advice, that we are on one side of the coin and we may not be fully aware of why we got there. So with that in mind, I'm currently an assistant professor at UTA, and I have known since the time I was about this person's age, 15, that all I wanted to do was physics. And I even knew at about the age of 17 that I wanted to do particle physics. So in that way, I'm exceptional in that I've had a direction and I've been lucky enough to always head in that direction. I didn't go to any sort of exceptional schools. My high school was a small town in Iowa. I went to the University of Iowa, which is a fine college, but nothing super great. I went to Texas A&M for my PhD, which was a great opportunity. Luckily, when I was growing up, Fermilab was in my backyard. Fermilab was 2 hours away from my home, so I got to visit there as a teenager and sort of be motivated by it. And that's how I knew I wanted to go to a PhD program and then go to Fermilab. And then I lived at Fermilab for 8 years, actually where I met both Dr. Woodruff and Dr. Jones working on one particular experiment that was there. So, you know, advice for somebody who's 15 years old is, of course, consume as much of your curiosity as you can, as broadly as you can, because it's rare if you know exactly what you want to go into, but also don't be afraid to go after it. If astronomy is a passion right now, then consume astronomy and learn the skills. And you might be surprised. It might take you somewhere else, but it could also take you in the direction that you think you're heading.
Thank you. Dr. Jones, would you mind?
Cool, yeah. So yeah, my backstory, I guess, is I'm from Hereford, England, which is a town without a university in sort of farming country in England. I guess I was just always really excited about science. I didn't always know I wanted to be a physicist, because I guess I didn't know that was a career. Like, you know, I liked computers, and like I maybe thought I wanted to like make special effects in movies or various other like scientific-y things. Then eventually I found out that it was possible to have a career doing research and just working to understand things about the universe. And then it was immediately clear that's what I wanted to do when I found out that was a possibility. So I then went and did my undergraduate in Cambridge. I'm the first in my family to go to university as well, so that was a strange experience figuring out how that all worked. But I went to undergrad in Cambridge, and then I did graduate school at MIT, and now I'm an assistant professor at UTA. So my advice, I think, is just even if it seems far-fetched, just go for it. Like just learn it and push. As soon as you have the opportunity, like reach out when you're in high school, even an advanced high school student, reach out to your local university and ask if there are opportunities to be involved in the science that's going on. We've had high school students working in our lab, for example, at UTA in the past, just learn a lot, get involved, and do well in school, and apply to do physics at university, preferably UTA.
All right, Ibrahim, would you mind saying a little bit of your backstory and advice for people?
So I'm originally from Lebanon, and I moved here at 17. Actually didn't move here for school. It was for other reasons, and I never finished high school. I kind of just went to community college and, for a few years. I've always been into physics. I always knew I wanted to do physics, but things have kind of, strayed me away from it several times. But then a few years into community college, I decided it's finally time to pick what I wanted to do. And I transferred to UTA and majored in physics. And that's where I met Ben, who was, I think, a postdoc at the time, and he was looking for research assistants. And I didn't even know that physics was a career, like Ben said. I just thought it was a cool thing to do, and I needed a degree. And so he kind of taught me that, there is a career there, and you could work towards it. And so I was doing some research at UTA, and then I applied to the University of Wisconsin, where I'm now a PhD candidate. My advice would just be to just kind of do what you like doing, and the opportunities will present themselves in time. You just need a lot of patience and a lot of hard work, and put your head down and kind of wait for good things to happen, and they often do. So.
All right, and lastly, Dr. Woodruff.
So I totally agree with all the advice here. I definitely didn't start at a young age being interested in physics. I didn't know what physics was. Even when I was in school, I did the same thing as Ibrahim. I went to community college for a few years. And I was just majoring in math because I was good at it, so it seemed like a good idea. And I ended up just being required to take a physics class, and basically in the first lab, fell in love with it. I was like, oh, wow, this just uses math to predict the universe like perfectly. That's amazing. And so from then on, I knew I wanted to do physics. So like they were saying, you just kind of, following my interests. And then I went on to finish, a 4-year degree, and then went to grad school in New Mexico, where I was introduced to particle physics at that point. Again, just kind of lucked into it. My advisor was joining a new experiment that both Dr. Asaadi and Dr. Jones were on, where I met them. And I got to spend a lot of time at Fermilab, which kind of made me fall in love with particle physics. And now I'm a postdoc at UTA studying neutrinos. So,
right. Thank you. Okay, so we have several more questions. They are all over the place, which is absolutely wonderful. So I'm going to give up on trying to organize these. I'm just going to have to ask them, and we'll have to just backtrack sometimes. So one that I think is a fantastic question is, how can small experiments be applicable to the universe? And so this one is hard for me to really assign to anyone because we all work on small experiments. But we also work on large collaboration experiments. So I think, Dr. Asaadi, if you don't mind maybe talking about sometimes how we do the small experiments at UTA and how it ends up applicable to all of the sciences.
Yeah, so there are some scientific questions which are best addressed in large collaborations with massive amounts of resources, all pointed at trying to answer some very deep and difficult questions, which is why we come together to collaborate in this way. But often along the way, interesting physics that that maybe is not deemed as important in the short run just to come up, and these big collaborations often don't have time or really the interest to go after those. And so these small experiments can dive down into them. And a lot of times there is more in the small questions than a lot of people give credit to. As to why does a particular thing work the way it does, or why does the signal look like it does, or we're doing things in a certain way, can we do them better? And that's oftentimes the questions that can be first addressed by small researchers. And what I find really exciting about a lot of the research we do at UTA is, we're working on not just current generation experiments, but thinking about things that will be built 10 and 20 years from now using technologies that we are inventing at the moment that are best done in these kinds of small, very dynamic teams that can go after these new ideas. So you definitely need both. I'm not disparaging large collaborations, but I find the small collaboration environment just exhilarating because you can try a bunch of really crazy ideas, and many of them just fail miserably, but that's fine because it's a small group of people just trying things. So that's a good way of getting science done.
Can I add a comment as well? I want to tie it back to this thing I mentioned in my talk about the way the scientific process works, right? There's like different stages in that process. There's like formulating the hypothesis. There's then making predictions and then testing the hypothesis. And often to test these like big picture questions, we do need these experiments that cost hundreds of millions of dollars and require like hundreds of people. So the ice cube experiment that I showed you, I mentioned that Ibrahim and I both work on it, but it's not just us, it's us and like 200 other people. And those other people are in Germany, Sweden, the US, all over the world. And we all work together and collaborate for a few reasons. First of all, in order to build something of that scale, you need multiple nations to come together to invest in the research question. But also the science is so difficult to analyze the data that comes out of that device. You really need the work of, you can't just do it on your own with a pen and paper. You need the work of hundreds of people working to understand what the data means because it's so complicated. On the other hand, the scientific process also involves coming up with like new technologies and new experiments and also new theoretical work, and that kind of work you can do in a smaller team. And I think if you're a really good scientist, you're involved in all of those aspects of the process. So you do some work with the big collaborations and then some work with a small team, and get the benefit of understanding from all of it.
Thank you. So this next question, I'm not positive who it should be aimed at, but I feel like Ibrahim has probably nerded out on this a few times. Could you speak to any new research or hypothesis on any relationship between gravitational waves and neutrinos?
Right. So there's actually an entire program that is dedicated to do correlation studies between gravitational waves and neutrinos. So we have a group here at Wisconsin and a group at Columbia University who are working on real-time follow-ups. So what we do is we have an agreement with the LIGO experiment, which detects gravitational waves, and they send us an alert as soon as they find something, and then we take their maps and we look for neutrinos coming in that direction. And so far, we have not made any significant discoveries of any correlations, but the LIGO experiment is only getting to its peak sensitivity just now. There's been several upgrades to the experiment. And the next run, this run got stopped short because of this pandemic, but the next run will have a lot more binary neutron star measurements, which are the ones that you suspect neutrinos could be coming from, because in a neutron star environment, you have very strong magnetic fields, and then usually there's a lot of matter surrounding these objects. And so there are many models that predict what kind of neutrino flux you expect from these. And so as soon as we see, I think we've seen only 1 or 2 of them so far, binary neutron star mergers. The most gravitational wave detections have been black hole mergers. And so maybe I would say in the next 5 to 10 years, we could have our first correlation. It's very exciting, and it's happening, at LIGO and IceCube and several other institutions.
Thank you. So this next one I think is very good for Dr. Woodruff, and I believe it's talking about one of the past Nobel Prizes of why is neutrinos having mass important?
So neutrinos, they're originally predicted to not have any mass. We know they're very light because of the spectrum that they were first measured in. But the fact that they do have mass is what allows them to oscillate between flavors. So basically, there's 3 flavors of neutrinos that we know about. There's electron, muon, and tau flavored neutrinos. And there's also 3 masses that the neutrinos can have. We don't know those masses yet, but we know that they exist. And the thing is that when you define the flavor of a neutrino, then you can't define the mass of the neutrino, and vice versa. So when you define the mass of a neutrino, then you can't define the flavor of the neutrino. It's in some superposition of the 3 flavors. So it's this really weird effect that's only possible because neutrinos do have mass. And so it's what causes neutrino oscillation. So if a neutrino is traveling through space with a known mass state, then it's oscillating between the different flavors it can have. So that's kind of what's really cool about that.
Thank you. So his next question is definitely made for Dr. Jones. Is the idea of parallel universes referred to at the end of the talk the same as the many worlds theory or interpretation of quantum mechanics, or are they different?
Yeah, no, when I was talking about the parallel universes that we really know about, I was talking about the many worlds interpretation of quantum mechanics. The one that the CPT universe, the model predicts, is a different thing, which is not the same as the many worlds interpretation. But yeah, that person got it exactly right.
So can I ask a tangential question then? Could there be many world CPT symmetric universes?
I mean, presumably the CPT symmetric universe would obey quantum mechanics. And so, yes, I think.
So y'all have actually mentioned CPT symmetric several times. Could y'all quickly summarize that, please?
Raheem.
Raheem, you're the one who said it.
Yeah, not it.
Well, there are these 3 fundamental operators, charge, parity, and time. And what we've observed is that they are invariant, which means if you apply all 3 operators to a state, you get back the same state again. And so that is something that is an empirical fact. And so the thing about, CP describes space, and T describes time. And so, given that you have this conservation law that is CPT is conserved, this idea comes about of, what if there's a symmetry there, and then you have these 2 universes where in one of them CPT is even, one of them CPT is odd, and therefore it's symmetric, and that's where the conservation law comes from. So that's where that idea comes from. But CPT is generally just a particle physics operator that you apply to states.
Let me try it without the word operator. Is that okay?
Sure.
So those things, CP and T, are all names of symmetries. And the symmetry is something you might have an intuitive picture of what it means, right? Like something that's square, like this. I luckily have a black square on my desk.
Yeah. What?
This square is looks the same if I turn it 90 degrees, or indeed it looks the same except it's got a label on the back. But it looks the same if I flip it 180 degrees, right? So parity is a symmetry, which means that this square P, parity, is a symmetry, which means that this square is the same if I move all the coordinates through the middle and out the other side. I sort of invert it somehow, invert the image, like a mirror almost. So that's an example of a symmetry. And the reason it's a symmetry is because the thing looks the same after I do that as it did before. So the universe that we live in is, in fact, not quite parity symmetric. We used to think it was, but there are particle physics effects that violate that symmetry. That mean if you invert the universe through a point, then physics behaves slightly differently. It's the weak interaction in particular that violates that principle. C is another one. So C is the operation of changing. I said I wasn't going to use the word operation. Sorry. C is the process of taking all of the positive charges and replacing them with negative charges, and vice versa. So instead of an atom having a proton with an electron going around it, it would have proton with a positive charge with electron with a negative charge. It would have a proton with a negative charge and an electron with a positive charge, right? And you can imagine that would behave basically the same, right? It's still going to be bound, it's still going to have the same kind of behavior, spectroscopy, so on. And if it really is exactly the same, then it's C symmetric, it's symmetric under C. And then T is time reversal. So the laws of physics on microscopic scales behave the same if you reverse the direction of time as if you have time going forward. Now, we actually know that all of those on their own are not quite true. Those are not quite good symmetries in particle physics. Parity is not quite a good symmetry because weak interactions break it, and same with C and T. But it seems to be at the moment that if you do all three things, flip the direction of space, flip the direction of time, and flip all the charges, then you should get back the same kind of physics in the universe that you started with. That's called CPT symmetry. And that's actually a deep prediction. And actually, I don't even really claim to understand how that prediction comes about. It's called the CPT theorem. It's quite a complicated theoretical physics thing. But that theorem suggests that CPT, all three of those things, would result in a universe that behaves the same way. If you change the charges, change space, and change time all at once. And so that's what the CP and T are. Now, the CPT symmetric universe means that instead of just hypothesizing the universe would behave roughly the same way, if I flip the charges, flip the space, flip the time, it's saying there is another universe that exists with the time going backwards, the opposite charges, and the opposite directions of space. Okay. So that's what that model means, right? It means there's another one that actually exists with all those things swapped.
Okay, so we actually have still quite a few more questions, which is wonderful. As long as y'all are asking questions, these people are stuck answering them. They have nothing.
I'm going to pour another beer, though. I'll be right back.
Okay, well, the next one is actually aimed at Woodruff, so that is fine. Well, it's not aimed at Woodruff, but it should be. What kind of detectors would be needed for double beta decay detection? Sorry.
Yeah, okay. So the detector, so the main thing for detecting neutrinos double beta decay is that the difference between an ordinary double beta decay event and a neutrinoless double beta decay event is that the energy of this decay has a very precise single value that's at the high end of the ordinary energy spectrum. So for normal double beta decay, you have this kind of energy spectrum that has a tail that ends at a given energy. And in neutrinoless double beta decay, that event would be exactly that energy. So we look for those events by looking for events in excess of events with exactly that Q energy that we're looking for. So the detectors we need would have very, very high energy resolution. That's the main thing, because the smaller energy window you can look at, the less backgrounds you have, and the more precisely you know the energy. So there's a ton of different technologies out there that are looking for it. We're using gaseous xenon time projection chamber, which is special type of detector that's been around for a while. Actually, our Dr. Nygren at UTA invented time projection chambers. But so these detectors are one way to do it. Other people use these special type of crystals that measure the change in temperature to get the energy. There's also liquid xenon time projection chambers and other things like that. Or huge detectors with special material in it that lights up when charged particles go through according to the energy of the decay. So, yeah.
Perfect. So this next question is also for you, Dr. Woodruff. Is the ratio of matter to energy in our universe very large? And if so, is it because of what we observe as matter today is only a small part of it what once existed? So talking about the asymmetry of matter to antimatter.
Oh, okay. So, so it seems like there's kind of a couple questions in there. So first, the ratio of matter to antimatter is actually very large. It's strangely large, right? Because if you expect everything to be the same in the early universe, and if if matter and antimatter are created equally and oppositely, then you would just be left with nothing. And instead, we have a universe made almost entirely of matter, based on what we observe in the stars and in everything around us. So the ratio of matter to antimatter is really large. The ratio of matter to energy is actually very small. There's a lot more energy in the universe than there is matter. The universe is mostly empty space. And if you include stuff like dark matter and dark energy, then the actual matter that we can see is some small, a few percent of the universe. I don't know if that kind of answers the question, but.
If not, if you will, Nico Mir, right at the end, what clarification you want, we will come back to it. So this next one is directed directly at Ben, or Dr. Jones. Can you talk more about these particles that move both forward and backward in time simultaneously?
Oh yeah, sure I can. That's kind of my jam, so I'm happy to talk about it. Yeah, so this whole idea that there was stuff that would go backwards in time as well as forwards in time was actually predicted before it was observed. It was predicted by a guy called Dirac, who maybe you've heard of. But Dirac was not trying to do anything to do with antimatter. He was trying to understand how quantum mechanics and special relativity, Einstein's theory of special relativity, could be put together. And he came up with a way, and his way of putting them together predicted there should be stuff moving backwards in time. And that was weird, because nobody had seen such a thing. But actually, it was pretty interesting that just a couple of years after he came up with that, it was found that at very, very small quantities, there is this stuff which seems to be like matter but moving backwards in time, called antimatter, that is around. And in fact, the positron was detected like 4 years after Dirac came up with this theory. And so for a long time, we've understood that like massive particles, or massive at least spin half particles, but can either be in this mode where they're going forwards in time, where they're called matter, or this mode where they're going backwards in time, where they're called antimatter. Now, there was a contemporary of Dirac's called Ettore Majorana, who came up with a similar but different way of combining quantum mechanics and relativity together. And actually, it fits neatly, packages neatly into Dirac's theory as well, but it can be expressed independently through something, instead of using the Dirac equation, using something called the Majorana equation. And this predicts that in any given system, there can be a particular, how do I want to say this? There can be particular parts of the quantum system which are going forwards in time, and other parts of the quantum system which are going backwards in time, and they both have to be there all the time. So you can never have a particle which is only like the one moving forward in time, like an electron, or one that's only moving backward in time, like the positron. You can only have this thing which would be called the Majorana fermion, which is really doing both at the same time. And so the only particle that could be one of these actually is the neutrino, because you can show that no charged particle can have this property. So the neutrino is the only known uncharged particle, fundamental particle. And so it's the only one that could be this thing that's both going forwards and backwards in time at the same time. And so it's actually a question of great physical interest whether the neutrino is one, because if it is one, it sort of helps us to explain this very strange matter-antimatter asymmetry that Katherine mentioned in her answer before. Dr. Woodruff mentioned, sorry, in her answer before. We work together, so we use first names, obviously. It's actually a prediction of the theories that explain why that is the case, that the neutrino would be this thing. And so that's why it's the focus of major research programs worldwide, which we're involved in.
Thank you. So this next question, I'm going to let y'all volunteer to answer because I don't have an opinion on it, so hopefully I'll do. Do you have any thoughts on Eric Weinstein's geometric unity theory of everything?
So I don't know the claim.
Yeah, I don't know the theory. I don't.
Never heard of it.
Yeah.
So I will tell everyone who's watching right now, the majority of us, I think, Ibrahim, you're also an experimentalist and not just a theorist, right? So that might be something.
Just a theorist. I like that.
I think a few of us know quite a bit of neutrino theory, though, right? And particle theory.
Yeah.
So I'm not familiar with that particular claim. So that person should post some reading material, and we can have a look.
Yeah, Joel Roberts, if you give us some stuff, we will absolutely gladly get back to you on that, or they will. Okay, so this next question, I'm actually going to have each of you answer it. I think it's a great question. What is the most crucial part of the scientific mindset? So the question is kind of wondering what the best attitude is when attempting to answer a question nobody knows the answers to. And so we'll do roundtable on this. Asaadi, do you want to go first, or we can have someone else?
Sure. This is. If I were to explain the method I approach a scientific question, it ultimately defaults to the scientific method, but I start in a very different space than I think a lot of people do. So I often think of the poster, I want to believe. Like when I hear something, I want to understand, and I want the extraordinary claims to be true. But then I often walk backwards, and I sort of have this opinion when I'm reading a paper or I'm approaching a scientific question of like, trust but verify. If somebody brings me a result, I want to believe it, but I want to also see the background. And then I ultimately find myself in the place of Carl Sagan's quote of like, extraordinary claims require extraordinary evidence. And that process for me sort of runs in a loop all the time. I'm enthusiastic about science, and so I want somebody to have found a parallel universe where time runs backwards and all of these things. And so I approach the question enthusiastically, meaning I want to understand what that person's saying. I think what Dr. Jones sort of walked through in his approach to it of like, this is an article I should know something about if it is true. These are people that I know that are working on this, and therefore maybe discredit the claim. I think that's an important process, and I hope that that's something as I continue as a scientist I maintain, but that enthusiasm sort of allows me to get up every day and like the job that I go to. So that's sort of for me, the most important part of the process.
All right, Dr. Jones.
Okay, so yeah, I guess I have strong opinions on this question. Like, the most important qualities for what was the actual phrasing of the question as these, so I can address it like properly.
I scrolled down to the next question. What is the most crucial part of the scientific mindset? Okay,
yeah, good. Yeah, so basically, I always think that by far the most important thing for making a good scientist is enthusiasm. And so I see this with students and people I work with, like the people who are just enthusiastic and dedicated and hardworking and just really drive to understand do really well. I mean, there's really no such thing as intrinsic intelligence. That's like a very old-fashioned myth that should be like consigned to the trash can of history. Like none of us on this call are intrinsically intelligent. We're just like people who got really, really excited and enthusiastic about something and then like really work to learn about it, right? And so nobody should ever feel like they're not intrinsically intelligent enough to do something. So enthusiasm is the most important thing. But also the second thing I think is just the willingness to believe that just because a problem hasn't been solved by somebody else, that means that you won't be able to solve it. Because you could be the first person to solve it, right? That's perfectly viable. And so a lot of people fall into that trap of thinking, this is a hard problem that loads of people have been working on for a really long time. So what hope do I have? but you have plenty of hope because at some point somebody is going to solve it, and it might as well be you. So I think enthusiasm and believing in yourself are the two most important things.
All right, Ibrahim.
I have nothing to add to that. I think that was the answer I would have given, slightly worded differently, but yeah, enthusiasm, definitely. Like, just make sure you're excited about what you're doing and wanting to wake up every day and think about these problems. But that's yeah, nothing further. I think Ben put it really well.
All right, Dr. Woodruff.
Yeah, I mean, yeah, I totally agree with what everyone else has said so far. I mean, I think everyone that's kind of still doing this for a living are the people that are just like way too excited about, the possibility of something crazy being true, So yeah, I think, yeah, I agree. That's what.
If I could also add a little bit here, because since we're all experimentalists, I think you also have to have just the willingness to fail constantly, because nothing works. And like, it takes a certain mindset of a person to be fine with going in the lab for that day and saying like, everything I'm going to do probably won't work, but I'm eliminating all of the bad stuff to ultimately find the thing that does work. And that's a very important mindset to have. And if that's not a way that a person works, like, you can certainly train yourself to think that way, but it also tells you a little bit about like, should you be going into this endeavor? If you hate failing all the time, I often tell people experimental science is probably not for you, because you spend so much of your time failing. But I enjoy it a lot, as much as one can enjoy being wrong constantly.
I definitely appreciate that. Thank you. So this one is going back to the many universes theory. So we're back to Dr. Jones. Actually, the next two are both going to be for you. So many worlds and many universes and many opposite universes, would those be created every time we make a measurement?
Okay, so in terms of the many worlds theory of quantum mechanics, it's a slightly old-fashioned way of understanding quantum mechanics to believe that the measurement itself is really important. And some people still teach it that way at undergraduate level. I certainly don't teach it that way when I teach quantum mechanics. In fact, that's something called the Copenhagen interpretation of quantum mechanics, which really makes the measurement something fundamental. But the universe would be behaving just the way it is, even if we weren't measuring it. I mean, these things are like bifurcating and branching and evolving, and it's just part of what quantum mechanics does. So really, like, our decisions and our measurements are not that important to the way the universe evolves. Really what happens is that just waves of probabilistic possibilities emanate. So the universe is like how it is at some moment in time, and then every possible thing that can happen starts happening, and the sort of those histories just like diverge and diverge and diverge from any given point. So that's the way I think about it. Like, I de-emphasize the role of measurement in understanding the parallel universes.
Okay, so this is from a different person, but also multiverses. So wouldn't infinite multiverses require infinite energy and define entropy and energy conservation? Where does this energy come from to fork at decision points over and over again?
Oh, great question. Really great question. So the energy in each of those possible universes, one imagines, at least, not having thought about it too much, thinking about it on the spot, but one imagines that all of those possible universes have the same amount of energy in, because energy is a conserved quantity. But the important point is that they don't all exist simultaneously, in the sense that you have to have all the energy to make them all real at once. I mean, if you have any particular experimental question to ask, you will find that the answer you get is consistent with one of those universes having been real. Okay, and so you don't need the energy available to realize them all. Really, the quantum mechanics is just realizing the potential of them all, let's say. So you only need the energy to make one of them.
Okay, thank you. So this one's from Jacqueline Johnson, and I have a feeling we should do this roundtable. What is your theory on dark energy? So, Dr. Asaadi, would you like to go first? We can also reverse it if you don't like being first every time.
It's with the last name of A. It's been my curse my entire life.
I feel like it's meaner for Katherine to be last every time.
Yeah, Katherine, please, why don't you actually start this? Because Yeah, this one right. I don't have a good one to go on.
If you don't mind, what's your theory on dark energy?
I personally do not have a theory on dark energy. I think dark energy kind of represents just this this huge frontier that's out there of just like, you know, just so many more questions to answer for the rest of our lives, at least for me. Like we have so little information on it right now that it could really be anything. And it just, so to me, what's really exciting about dark energy is it means that just like there's so much more out there to discover that we don't know, which is like exciting. That's kind of how I view dark energy right now.
Do any of y'all have something you want to add?
I mean, I can give the like basic like elevator pitch about what dark energy might be, I suppose. So quantum mechanics, in quantum mechanics, systems have a certain amount of energy you can never take away. It's called the 0-point energy. And so like in classical mechanics, you can take a rolling ball or something and put it at rest. So it's stopped. It's got no energy. In quantum systems, that can never happen. You can never really stop something because you can never know both where it is and how fast it's going at the same time. It's always got some amount of 0-point energy you can never take away. And the quantum mechanics and quantum field theory actually predict that all of the 0-point energies of all the things in the universe should be present as this like dark energy background, which is everywhere. Just all the energy of all the stuff that you can't take away is going to be all over space. The problem is that if you predict how much there is, you get the answer wrong by 120 orders of magnitude. And when we do the observations astronomically and look at dark energy, we see 10 with 120 zeros, the wrong number compared to what quantum mechanics predicts. So it's wrong. People come up with various beyond standard model theories to try and make corrections for this, but nobody really has a very good solution to it at the moment. My own suspicion is it's probably something to do with our misunderstanding of like how gravity emerges from quantum mechanics, I suspect. But I don't have a well-formulated theory with a capital T, at least.
Okay. So this question, actually, I think I asked it wrong earlier, but this is back to Dr. Woodruff on the disparity between matter and so the question is, if the disparity between matter and energy is so large, then is the remaining matter today a small part of what once existed? So do we start with more matter and antimatter? And that just annihilated itself, I think.
Yeah, I don't know if I totally understand the question. I mean, the idea in the Big Bang is that we started with the energy that we have today, right? Yeah, I guess I don't really understand.
I mean, there did used to be a lot more matter and a lot more antimatter. So there used to be 10 billion and 1 parts of matter for every 10 billion parts of antimatter early in the universe. And the 10 billion annihilated each other, and that's the cosmic microwave background radiation that I talked about in my talk. That's what you see, is the energy left from the annihilation of the matter and the antimatter. And it's the 1 part in 10 billion that's left that is like the Earth and the stars and the galaxy and everything, and us.
So does that mean there used to be like 1 billion times more matter in the universe before it was annihilated?
Yeah, there used to be 10 billion times more matter than there is now before it annihilated. Yeah, I think.
But it is true that you have the same energy. Well, with the exception of I guess dark energy is always adding energy into the system, right? So you don't lose energy. The matter that annihilates turns into energy, but so those are equivalent, but the dark energy is what adds energy to your system, right? Yeah.
Perfect, thank you. This next question I think is perfect for Dr. Asaadi. Where do neutrinos come from?
Okay, so everything essentially is the answer. So you've got, anytime you have a process which involves nucleus undergoing radioactive decay, you're going to find neutrinos there. So the process in the sun is one that creates neutrinos. You have any sort of unstable element. That element, when it then goes to a more stable state and wants to, by releasing its energy and changing its nature, will release neutrinos as part of it. You hold a banana in your hand. That banana has potassium in it. Potassium is an unstable isotope and will emit neutrinos. So you'll get neutrinos from a banana. you have neutrinos actually coming from the Earth. There's this process called geoneutrinos that comes from the uranium and other radioactive elements in the Earth's crust from the heavy elements that were created when a star exploded and then ultimately condensed down into the Earth as we know it gravitationally. And we can learn about the nature of the mantle of the Earth by studying the properties of these neutrinos that come from the Earth. When we create artificial radioactive sources in nuclear reactors, like Dr. Jones showed, you can get neutrinos there. There are neutrinos that come from supernova. So actually, when one of the brightest, most violent events in all of the universe is when a star explodes at the end of its life. But it turns out that 99.9% of the energy of the star that's being released is actually released in neutrinos. And just the energy that we see that can light up a star so bright you see it in the daytime sky if the supernova is close enough is actually just a small fraction of the total energy. So there were neutrinos created in the very, very early universe at the moment of the Big Bang that persist and float through us all of the time, but they are just so difficult to detect that we've never detected them. So neutrinos are everywhere. They are the most abundant matter particle by many orders of magnitude, and they come from everywhere. They come from everything. So that's what makes them kind of fascinating in that way, is if you want to understand the puzzle of the universe, study one of the most abundant things.
Perfect. So we are actually on our last question now. I'm going to allow y'all to volunteer to answer it. I think I know here. The question is, what's your opinion on Stephen Wolfram's new way to see physics?
I can have a go at it if you want. I think I'm probably sure we share the same opinion. It doesn't make any predictions, so it's not a scientific theory.
Perfect. All right, so it doesn't look like we have any more questions. If any of you do have additional questions, if you follow us on any of our social media and message us, I will make sure to transfer it to the correct person and get you the answers that you need on it. Also, underneath our video description, if you click on any of the links, it should take you to our social medias. We do appreciate being followed. And if you go to our website, you should be able to message us directly if you don't have any of the social media. So I do appreciate all of y'all attending and coming to this. I think we will probably do them again in the future. If you have any articles that y'all find interesting that you would like more discussion on, if you again send those to us, we'll look through them and see if we can find a panel of experts to talk about it. But until then, thank you all for coming and try to stay safe.
Peace.
Cheers. Thank you.
Bye-bye.
Bye.
We're going to unstream us, Ben. We unstream.